Hey guys, welcome to the recitation number 11. So today we will solve some problems about some problems with sequences of real numbers. Like I said, next week we'll talk about series of real numbers. And I was planning to do, well, I was supposed to post on my website the worksheet, but I haven't finished it yet because I want to update it with more problems. And now I look at the previous homework, and there are some 4 problems that I would like to discuss. All right, so let's get started. Sorry about that. Okay, so the first problem that I have in mind is the following. Okay, the first problem is problem 1 is the following, is to find the following limits. Okay, the first one is the limit as n approaches infinity of n times log 2 minus this sum and the second one is the limit as n approaches infinity of 1 over n, the sum of the square root of 1 plus k over 1 plus 1 over k plus n to the power n. Okay, so this is the first problem that I would like to see. Now, so let's solve the first one. Part A. Well, first of all, I would like to ask you, what kind of indeterminate do we have? Can you tell me?
Infinity times 0?
Infinity times 0, right? So maybe we could do something about it, such as, well, do you remember I gave you this so-called Cezar-Stolz lemma? Infinity over infinity. So we intend to apply the Cezar-Stolz lemma, but this time 0 over 0 case, and I haven't discussed it in the lecture, but I'll do it now. 0 over 0. This is important. And let me see what, so let's state this. So lemma, let me just say Cezar-Stolz 0 over 0 case. All right, it says the following. So let an be n and bn be 2 sequences of positive reals such that an is decreasing to 0 second condition, the limit as n approaches infinity of bn is 0. And the third condition, so just like in the infinity over infinity case, there exists the limit as n approaches infinity of an over bn, an plus 1 minus an over bn plus 1 over minus bn equals to L. And this is a number in R bar, right? But then the lemma states that then there exists the limit as a, let me write it with the same color, then there exists the limit as n approaches infinity of n over bn equal to L, right? Just like in the infinity over infinity case, this 0 over 0 is basically the same, right? So this is the discrete derivative here, delta n. So this is discrete derivative. It's just like L'Hopital rule that you learn in Calc 1. And the same goes for this one, delta bn. It's the derivative of an, and this is the discrete derivative of bn, right? So it's the same thing. Okay, that's great. So let's use this lemma. I want you to look at it. So we would like to use this lemma. So let's go back to our sequence. So we have that limit as n approaches infinity of the n times log 2 minus the sum is the same as limit as n approaches infinity of, keep in mind that the sum here from k equals 1 to n of 1 over k plus n converges to what? To log 2, right? To ln of 2. So we can write this in the following way. We have two options here, so I'll prefer this one. I think is better. One over n, right? And at this point, this is 0 over 0, so I can apply the Cezar-Stolz. So I have 0 over 0, and this would be nothing else than just the limit as n approaches infinity of what? Of, let me write it in this way, log 2 minus the sum from k equals 1 to n plus 1 of 1 over n plus k minus log 2 the sum. Everything over 1 over n plus 1 minus 1 over n. And this will be equal to, if you look at it, this will be lim as n approaches infinity of, and now let's see the last one will be what? So have 1 over 2n plus 1, right, minus 1 over 2n plus 2 plus 1 over n plus 1. Everything over 1 over n plus 1 minus 1 over n. Right? And now if we do some algebra here, oh my. This would be equal to, let's do it here. This is 1 over n plus 1 minus, and I can factor here. In fact, no. Wait. I can factor here 1 over n plus 1 times 1/2 minus 1. Sorry, 1 minus 1/2. Dang. Minus 1 over 2n plus 1. Everything over, and let's do some computations here. Negative 1 over n times n plus 1. And this, okay, the limit here. So this would be equal to the limit as n approaches infinity of so here I'll have 1/2 this is equal to, and now let's do some computations here. In fact, let me do it here. So have here it will be 4 over okay, let me So here I have 2n plus 1, 2n plus 2, and here I'll have negative 1, right? Here I'll have negative 1 times n plus 1. And if we, well, this would be, well, I don't want to do computations at this point. I don't want to embarrass myself with some algebra mistakes, but I think you can figure it out. What is the limit now at this point? Can you figure it out? Is what? What is the limit of this? Well, this is 2n plus 1 here, by the way. Is 1/4. That's it. Right? And that's it. So you see, Stokes-Cezar 0 over 0 case comes into rescue. Okay, let's see the second one. So the second one, let me consider the sequence. Let an be this guy, 1 over n, the sum from k equals 1 to n of the square root of 1 plus 1 over n plus k. Okay, and we're asked to find the limit of an to the power n. So we need to find the limit as n approaches infinity of an to the power n. But before we do that, we need to find the limit of n. First, we compute the limit as n approaches infinity of an. All right, let's look at this guy. I think we can use Stokes-Cezar here. There'll be no problem, but I prefer to do it in a different way. Maybe I will want to use squeeze theorem. So let's look at the first and the last term. So we have, let's see, what do we have? So let's look at n. So I'm gonna look here, 1 over n. In fact, let me do it this way. 1 over n, the sum from k equals 1 to n, 1 plus 1 over n plus k. And this is between these two. Let's here put here 1 over n times the first term. The square root of 1 plus, and now let's be careful. So k equals n, right? 1 over 2n, right? And here I have 1 over n times the sum, the square root of 1 plus 1 over n plus 1. Well, this guy here, let me look at this, and let me look at this. So this guy here will be the square root of 1 plus 1 over 2n, right? Because I have n of these. And this guy will be the square root of 1 plus 1 over n plus 1. So this guy is an. Okay, let me put here, let's equal that. Well, at this point, it's quite clear what happens. This will converge to 1. This is also converges to 1. And as n approaches infinity, this will converge to 1. So by the squeeze theorem, it follows that the limit of n is 1, right? Hey, Aaron, what's up?
Hey, Cezar. Sorry, I'm late, man.
No problem, no problem. All right, so that's the first part. This is the first part, right? And now the indeterminate that we have is that is 1 to infinity. And we need to take care of this. And I think we I don't know if I, anyway. So we have that, that the limit. So what we're going to do is the following, the n to the power n. We're going to do this trick with the exponential, with the Euler's limit. And this will be the limit as n approaches infinity. I think I have one of these type of problems in one of my GRE tests when I took it a long time ago. So it was very similar to doing something like this anyway. So this way I'm going to add and subtract 1. I'm going to do it like this. And this guy here, sorry. Mistake here. This is 1 over an minus 1. This is n times an minus 1. But this guy here, if you look at it, this guy, the limit of this guy will converge to what? Can you tell me as n approaches infinity?
E.
E. So this would be nothing else than just e to, so it will be the limit, let me put it this way. It will be the limit as n approaches infinity of e to n times an minus 1, which is equal to the exponential commutes with the limit, so it's e to the limit as n approaches infinity of n times an minus 1. So we need to compute this guy here. So if we compute this guy, then we're basically done. So let's see.
A comment.
Yes.
So it converges to E because you can set a sub n minus 1 to like some variable, and then that's the take the limit of that, and that converges to Euler's constant, right?
Because
N over to 1 over n.
So the limit as n approaches infinity, let's say of 1 plus an,
Yeah.
or let's say bn. Okay, let me put it this way: 1 plus this sequence bn, everything to the power 1 over bn is e. As the sequence bn converges to 0. So this is what we used, right? All right, and now let's take care of this guy. What about this guy? So let's see who is this guy. So let's denote bn times an minus 1. So who is this guy? So bn will be equal to, so n, so it's an minus n, which is equal to, and let's look back who an is. So it's 1 over n, with times n will be the sum from k equals 1 to n of the square root of 1 plus 1 over n plus k minus n. So that's my sequence. And now we can do the following here. So we can just do the same type of squeeze, right? We can neglect now, but you will see that you will not get what you want. And I'll leave this to you as an exercise to see.
I have a question. How'd you get that summation at the end there?
It's here. That's my sequence.
Sorry, yeah, I got here late. My bad.
Right? Okay. So now what we're going to do, we were trying to try to pursue the computations as much as we can. So what I would like to say, let's look at this term. So I would like to look at this guy here. So when we look at this term, so we have that the square root of 1 plus 1 over n plus k minus, you see? Okay. Let me, just a second. Let me rewrite this a bit, even better, so that you can see it is the square root of 1 plus 1 over n plus k minus 1. So I'm looking at this guy here. So when I look at this guy, and when I apply the conjugate, so I'll have here, look, I'll have 1 over n plus k over the square root of 1 plus 1 over n plus k plus 1. Okay, that's beautiful. So this implies that, so this gives us that Bn is equal to the sum of 1 over n plus k, everything over, oops, everything over the square root of 1 plus 1 over n plus k plus 1. Okay, and now we can do the squeeze. So our intention is to use the squeeze theorem, right? And now let's see, how do we use? You see, let me write it again. So let me write it in this way. This is this sum. And I'm just gonna look at the denominator here. I'm not just gonna, so I'm gonna look only at this guy here. I'm gonna leave the numerator alone. I'm not gonna do anything to it. So let's see, because I have to be careful here with the squeeze. So I'll try to, when you have this complicated fractions, so maybe it's a good idea just to have some common denominator. And well, we can do this. So I'll write it in this way. So this is the sum from k equals 1 to n of 1 over n plus k. And I want you to be very, very careful here when I write this. So the largest term, so here I'll have what? 1 over 1. And I have, so let's see, what do I put here? N plus 1, right? And here I'll have the same thing. The square root of 1 plus 1 over 2n plus 1. Right? Agree with me? I hope I didn't do any mistakes in computations. Or if you want, so, okay, let me write it again. So this guy is our sequence. Let me, this will be greater and less or equal than. And here I will put this guy 1 over the square root of 1 plus 1 over n plus 1 times the sum from k equals 1 to n of 1 over n plus k. And here I'll have, I'll take this one out. Times this sum. Okay, I want you to tell me now. This guy will converge to what? And this guy will converge to what? So let's do it step by step. This guy here will converge to what? Only this guy. Can you tell me?
1/2.
1/2. And this guy here will converge to, do you remember?
Log 2.
Exactly, log 2. And the same goes for this guy here. This is log 2. This is log 2. And again, this will converge as well to 1/2. Well, at this point, it's quite clear. So this will converge to log 2 over 2. And by the squeeze theorem, this will converge as well to log 2 over 2. You see? Or if you want, so the limit as n approaches infinity of Bn is log 2 over 2. And thus, this will imply that the limit as n approaches infinity of an to the power n will be e to the power log 2 over 2. Or if you want to write this, We can go even further. This is e to log 2 to 1/2. Yes, which is square root of 2. And that's it. That's the end of the problem. Does it make sense? Is it clear for everybody?
Yep.
Okay, good. Now let's see the second one. The second problem, if I look at the worksheet, is the following, was a Putnam problem. So problem 2. So my intention is to do 4 problems, okay? It says the following. Given a positive integer n, let m of n be the largest integer m, be the largest integer m, such that we have the following inequality: m choose n minus 1 is strictly greater than m minus 1 choose n. And now we're asked to evaluate the limit as n approaches infinity of m of n over n. So this was a Putnam, what was it? A Putnam A2 in 2016. Okay, now I want you to look at the problem for a bit.
I have I guess a question. Or
Yes.
can we expand the that formula or that expression, essentially that choose expressions in terms of a factorial, I believe, right?
Yeah, that's exactly what you need to do. So you need to expand this by factorials, and once you do this, you will derive some inequalities there. And then you'll see that something happened to that largest m. It will be between something and something. So let's see. So we need to expand this. We need to look at this guy here. So let's write it. So remember that n choose k is n factorial over k factorial times n minus k factorial, right? And this implies that m choose n minus 1 will be nothing else than just m factorial over n minus 1 factorial times m minus n plus 1 factorial, right? So that's it. And now, and this guy, m minus 1, n, choose n, will be m minus 1 factorial over n factorial times m minus 1 minus n factorial. And now you write this inequality. As you can see, some of the things will just go away. And at some point, the inequality, and I'll leave this to you as an exercise, given, is equivalent with once you do all this, you'll get a quadratic equation anyway. And at some point, we'll get to inequality. It's equivalent with, let me write it in this way. I think I've done it here somewhere. Where is it? Just a second. Okay, so it will be mn, right? This will be greater than m minus n plus 1 times m minus n. Okay, so that's the first inequality. Or you can have a second one, which will be m squared, well, minus 3n minus 1 times m plus n squared minus n is less than 0. Right? Anyway, you'll get this. So these are the two inequalities that you'll get. It's just a computation. I'll leave it to you as an exercise to see why is this true. And now, by looking at this as an inequality, quadratic inequality in M, right? You will see that, well, you know that the quadratic function is negative. What happens to the roots? So M will be between the roots, right? So if you compute them, if you compute the roots here of the second one, right? You'll get something. So let me just say, treating two.
So what you're saying is like for the quadratic, you'll have two roots in terms of m, I guess.
Yes, you have m1 and m2, which will be in
Greater than
terms,
0.
yeah, which are in terms of n. Yeah, exactly. And you know that m will be between the two roots, right? It's negative. So the quadratic inequality is negative. This would be, will imply that m will have to be between the two roots, m1 and m2. So by using this, we'll have that, so by treating this like a quadratic inequality, we obtain that m will be between these two roots. So m will be between, and these two roots are, let me see, I computed them somewhere. So these two roots here will be between will be between something like 3n minus 1 plus a square root of 5n squared minus 2n plus 1, right? Everything over 2. And this will be less or equal than 3n minus 1. Oh my God. I hope it's not COVID again. 5n squared. Sorry, minus here and plus there. Minus 2n plus 1 over 2. You see? So that's what we obtain. So this is the first root, right? With negative, let's say m1 and m2. Just solve the associated quadratic equation of this, right? Of the second one. If you set it equal to 0, you'll obtain m1 and m2, the ones that I wrote there. Anyway, and now clearly this implies that well, let's see who m of n is. M of n is what? Is the largest integer m such that this inequality holds true, such that this holds true. So at this point, m of n will be nothing else than just what? If you look at it, is the greatest.
The squeeze theorem here once again. Just
Yeah, I'm gonna, well, not yet, but I want to identify who this is. So this is nothing else than just the largest integer of 3n minus 1 plus the square root of this guy, 5n squared minus 2n plus 1 over 2, right? So now, so this is the largest integer or Gauss function. So this implies that this will give us that m of n is between, well, you know, in that, okay, let me mention this here, that this guy is less or equal than the number and is greater than x minus 1. So keep in mind that we have this property and we're going to use this here. So by using this, so this will be 3n minus 1 plus the square root, oops. Let me write it here. So it will be, let me write it like this, net minus 1 here. So it will be 3n minus 1 plus the square root of 5n squared minus 2n plus 1, right, over 2, right? And less or equal than the same thing, 3n minus 1 plus the square root of 5n squared minus 2n plus 1 over 2. And now, if you look at the computations, if you use the squeeze theorem, this will converge to what? Can you tell me? As n approaches infinity. Oh, sorry, over n. Oh, just a second. Okay, not yet. Not yet. And finally, we get, and now let's divide by n. M of n over n will be less or equal and greater or equal than, this will be here 3n minus 1 plus the square root of 5n squared minus 2n plus 1 over 2n minus 1 over n. And this will be 3n minus 1 plus the square root of 5n squared minus 2n plus 1, right? Everything over 2n. And now, can you tell me what this converges to as n approaches infinity? What is the limit of the left-hand side or right-hand side?
3 plus the square root of 5 divided by 2.
Yes, 3 plus the square root of 5 divided by 2. And that's it. We're done. It was a very simple problem, huh? Very simple. In fact, it's just basic college algebra and, okay, some squeeze theorem and knowing what the binomial is. Anyway, so that's it was a Putnam A2. And now let me see another problem from the worksheet again. So problem 3. This will be important as well. And it says the following: let xn be a sequence.
I have a quick question.
Yes.
About the last one.
Okay.
So when we subtract 1 to enable us to essentially use a squeeze theorem.
Yes.
And
divide it by n.
Okay. How do we know like that this follows the range of like m sub n that we're not missing any values less than just -1 from this, so to speak? I don't know.
No, we just apply this here. So you see, this is the floor function, like the integer part, let's say, right? And it's
right. But I just remember that the problem was was defined in terms of like that function was defined in terms of some integers or like some sums of integers or something like that, right?
Yeah, you can find it in terms of n. Look, so you can write m in terms of n.
Yeah. Okay.
You see, m1 and m2. So this m here is m of n, which is between these two integers, m1 and m2, which are in terms of n. So you can derive, since they're consecutive, if you look at them, you can say that this is the floor function, right?
Gotcha.
And well, by using this inequality, then it's quite clear what to do.
Yeah, okay, but that seems like it's also continuous, right? If that and increasing.
Yeah.
Right?
Wait, I don't know, maybe, but I don't even care about that. I just care about the squeeze. I want to squeeze this.
Okay. All right.
Anyway, let me go back to problem 3. So this is a sequence of real numbers such that x1 is positive, and we will have a recursion here. Now, I think maybe I haven't done this, but xn plus 1 is xn plus 1 over nxn, right? For n greater or equal than 1. And we're asked to show that the limit as n approaches infinity of xn over 2 square root of 2 log n is 1. Okay. We have done something similar, right, in lecture. And now let's see how we deal with this. I want you to look at the recursion a bit, because here, when you pass to the limit in the recursion, we'll get a problem. We have an n here. I want you to look at it. Look. So it depends on n as n approaches infinity. So when you pass to the limit in the recursion, well, presumably that the sequence converges, whatever, you'll have some problems there. Well, I would like to ask you, when you look at that recursion, suppose that xn is convergent. If you pass to the limit as n approaches infinity, what do you get? Can you tell me?
Do you get x sub n?
So if xn converges, if xn converges to L, you'll get that there xn plus 1 will converge also to L, and you'll get L equals L plus 1 over n, but that's infinity already. So it will be 0. So you'll get 0 over L equals L, which is nothing. You understand what I'm saying?
Wait, you said as the limit as n approaches infinity, right?
Yes. But as n approaches infinity, if xn has
I see. Okay.
final
Yeah,
L, 1 over n xn will be 0. So now, maybe you see, passing to the limit in the recursion, well, presumably, like I said, that the sequence converges, doesn't give you anything. So maybe we should come up with something else. Anyway, we'll see at the right time. But first, let's see. We can prove that by an easy induction. Okay, by an easy induction. An easy induction. We can show that xn contains only positive terms. So xn is greater than 0 for all n greater or equal than 1, right? It's quite clear, right? So x1 is positive. Then assume that xn is positive. Then since xn plus 1 is xn plus 1 over n xn, since xn is positive, then 1 over n xn will be positive. So it will follow that xn plus 1 is positive. So by the induction, it follows that if we assume that xn is positive, it will imply that xn plus 1 is positive. And so by the induction principle, x is positive. So I'll leave this to you as an exercise. But basically, I just told you, but I'll leave it to you just in case you want to write it down. Okay, so this is positive. Moreover, it's quite clear that, it is quite clear that the sequence is increasing, right? Xn is increasing. That's obvious, right? I hope. Because xn plus 1 minus xn, let me write it here, xn plus 1 minus xn is nothing else than just 1 over n xn, which is positive for all n greater or equal than 1. That's the argument. Okay, so the sequence is increasing. It's bounded by below, but I don't know if it's bounded by above, but I could have a hunch. And my hunch is what? That the limit of xn is what? What do you think it is? What do you think the limit of xn is? Based on what you have to prove there. The only option you have there is like, is what? Infinity, right? Yes.
Yeah.
So now let's prove this. So assume by contradiction that the sequence is bounded by above. So assume by contradiction that xn is bounded. Well, by the monotone convergence theorem, it follows that xn converges to L, to some positive, negative number L. And now, like I said, if we pass to the limit in the recursion, we'll get L equals L. So there is nothing we can do. So what can we do? You see, this it's tricky here. So there is nothing we get from there. So now we're going to do the following. So now we rewrite the recursion as, so we're going to write it in the following way. So xn plus 1 minus xn, right? It will be 1 over nxn. Okay, that's great for n greater or equal than 1. But since I know, okay, but I know that this is increasing, it will be greater or equal than what? Then 1 over n x1. Xn, sorry, right?
Would be xn minus 1.
In fact, let me write it like, yeah, no, let me just write it in this way. For n greater or equal than 1. And now we're going to sum up everything. So for n equals 1, we have the following. So what do we have for n equals 1? So we have x2 minus x1 is 1 over 1x1. N equals 2, we have x3 minus x2 will be 1 over 2x2. We keep going. Let's say for n equals n minus 1, we'll have x n minus xn minus 1 will be 1 over n minus 1 xn minus 1. And for n equals n, we'll have that xn plus 1 minus xn is 1 over n xn. Okay, now we're going to sum up everything and look at them, how they go away. Boom, this with this somewhere here, this with this with this. And the only terms that will remain, will stand up here, right? The only terms are the following. Is this guy and this guy. So when we sum up everything, we will have that xn plus 1 minus x1, it will be the sum from k equals 1 to n of 1 over k xk. But now we're going to look at so this will be greater or equal than the sum from k equals 1 to n of 1 over k times xn, which will be equal to, this guy is 1 over xn, the sum of k equals 1 to n of 1 over k. But do you remember this guy, right? Do you remember this guy? This was what? The harmonic sequence. So, okay, let me write it here. So, xn plus 1 minus x1 is greater than 1 over xn times hn. Well, we assume by contradiction that the limit, so as n approaches infinity, xn will approach L as n approaches infinity. So it follows that, it follows what? It follows that L minus x1 is greater than 1 over L times infinity. Contradiction. Right? Because, or it will follow that hn is bounded, which is not true. Hn is unbounded, it's infinity. Okay. So this implies that hn diverges to infinity. Okay, but now we're asked to prove this. You see here, look back at the recursion. So we would like to prove this limit. And here comes the trick here that I want to mention. When I look at this, you see we have the square root, and you are tempted to apply Cezar-Stolz lemma, right? But you see, when you apply it in this way, you will be like, oh my, I have the square root there, so it's not convenient. So what you need to do, we will compute the following. So we compute the limit as n approaches infinity of xn squared over 2 log n. Anyway, the 2 doesn't really matter. So this would be 1/2 times the limit as n approaches infinity of xn squared over log n. And we have done something similar, right, in that problem, that Putnam B4 problem. Now we apply the Cezar-Stolz lemma. This is infinity over infinity here. And this will give us, well, it's 1/2. I always forget about this. This is 1/2 times the limit.
So I'll ask a question at the end.
Okay. So the limit as n approaches infinity of xn plus 1 squared minus xn squared over log n plus 1 minus log n. Right? And this will give us 1/2 times the limit as n, oh my God, I'm going over time, but anyway, xn plus 1 minus xn will be xn plus 1 plus xn times xn plus 1 minus xn, everything over log 1 plus 1 over n. But now, again, like I'm doing the same trick, so this would be 1/2 times, I'm going to multiply by an n. It will be n times xn plus 1 minus xn times xn plus 1 plus xn here, everything over log of 1 plus 1 over n to the power n. And this will be further equal to, as we pass to the limit as n approaches infinity, n times this will be 1 over xn, right, by the recursion, times xn plus 1 plus xn. And this would guide here, well, let me write it again, 1 plus 1 over n to the power n. And now let's pass to the limit, actually, to see what's going on. So this would be 2l.
E in the bottom, right?
Yeah, it's log e at the bottom, so it will be 1. And here I'll have 1 over l. Well, I should be careful here because the sequence is actually divergent, and maybe I should be careful here. Wait. Let me be careful. Let me rewrite it. So this would be the limit. So the bottom is 1. So this guy will converge to 1. So I can get rid of it. So the limit of the quotient is the quotient of the limit. So this will be the limit of 1 over xn times xn plus 1 plus xn. And this will be equal to, because I need to be careful here, of xn plus 1 over xn plus 1. And now I have to compute, so which will be, okay, 1/2 in front of it. So it will be 1/2 plus 1/2 times the limit as n approaches infinity of xn plus 1 over xn. But this guy will be, it's 1/2 plus 1/2 times the limit as n approaches infinity of, and now let's see who this guy is. Xn plus 1, if we go back to the recursion, xn plus 1, let's see. If we divide by xn, you see in the recursion, this would be 1 plus 1 over n xn squared. It will be 1 plus 1 over n x nx squared, which will be 1/2 plus 1/2 times 1 plus 0, which will be 1. Are we done? Not yet. Keep in mind what we computed. We computed this guy. So we need to take the square root of this. So this implies, so finally, we obtain that the limit as n approaches infinity of xn squared over 2, the square root of 2 log n will be what? Will be the square root of 1, which is 1. And yes, we're done at this point. And I think that's it. All right, Aaron, you had some questions?
Yeah, the Cezar-Stultz theorem,
Mhm.
is that the discrete version of like L'Hopital's rule? When you get an indeterminate, you can do that, what you just did, basically?
Yes, yes. It's exactly the discrete version of the L'Hopital. So you have the infinity over infinity and 0 over 0. Okay. All right, guys, I think I'm gonna stop here. I went a bit over time. I think you got the main idea of what's going on with the sequences of real numbers. And next week we'll talk about series of real numbers. You'll see that the series will be just a generalization of the sequences of real numbers. Okay, I'll see you